Hi everyone, thanks for coming to my talk, and thanks to the organizers for having me. I'm going to be talking about a topic that's near and dear to my heart. It's been something that I've been thinking about for almost 10 years now. The topic is semantic parsing for natural language interfaces. So let's unpack this title a little bit. So let's zoom in on natural language interfaces. And actually, let's go farther. Let's start with interfaces. By interfaces, I mean the way that humans interact with computers. And since the 50s, there's been enormous improvement in the ease and accessibility of our interactions. And in the last 5 to 10 years, we see a rise of natural language interfaces, virtual assistants such as Alexa and Google Assistant, which represent the first generation of something that I think will be very promising in the future. So now and what this is really about is accessibility. Out in the digital ecosystem, there's a lot of APIs and data. And what this is about is allowing users to access and harness the power of all these data and APIs in a much more accessible way. So now let's focus on semantic parsing. So semantic parsing is the process of turning natural language into programs. And let's go through a simple example. So what is the largest city in Europe by population? So it talks about cities. So suppose you have a set of cities. The sentence mentions Europe. In particular, it talks about things which are contained in Europe. In particular, it talks about things which are both cities and things that are contained in Europe. It has something about population. And in particular, we're taking the argmax of the set with respect to population. That is a program that when you execute it on the database of facts about geography, you can get the answer. So what I like about semantic parsing is that for question answering, it's interpretable. It gives you a provenance of how the answer was derived. And furthermore, it's compositional, just like natural language. Programs are compositional, but programs don't have ambiguity. And the role of semantic parsing is to resolve the ambiguity in the context and using pragmatics. So in general, the semantic parsing takes sentences and converts them into programs so that you can execute them to produce some behavior against a particular context. So let me start with a brief history of semantic parsing. One of my favorite NLP systems dates back to 1971. So Terry Winograd, when he was at MIT, he built a system called Shirlu. In Shirlu, a user interacts with a computer in the context of a blocks world environment. And you can have a dialogue, asking questions, issuing commands, and the computer can respond by taking actions and can also clarify. So this was really impressive for the time. It presents an end-to-end system for doing syntax, semantics, dialogue, and planning. So, but the next year, Terry wrote that this might be a kind of a dead end because the complex interaction between all these components, which give the program its power, also make it just extraordinarily hard to understand and extend. So in the 90s, we know that the statistical revolution took place in NLP, and it also hit semantic parsing. So Ray Mooney was the pioneer of bringing statistical methods to semantic parsing. He gathered this data set called GeoQuery, which had examples of questions and programs. And this was extended by a long line of work by Luc Zettermoyer, leveraging more powerful linguistic representations called CCG. And since there's been an increasingly amount of activity, and this is not an exhaustive list, but now we have a pretty healthy community of people who are interested in semantic parsing. So in this talk, I want to zoom out and think about the 4 aspects which I think are crucial for the success of semantic parsing. And for each of these, I'm going to talk a bit about the work that I've done over the last 10 years that helps make us make some progress in each of these areas. So let's begin with data. So going back to the 90s or 2000s, if you look around at data sets for parsing and machine translation, they had a fairly robust number of examples. But if you look at semantic parsing, you only had less than 1,000 examples. And so for much of the history of semantic parsing, it was really data starved. And of course, data is kind of necessary to do kind of anything interesting, statistically. So when I first started working on this problem in 2010, 2011, I wanted to kind of address this problem. If you look at the type of supervision that semantic parsing at the time demanded, it was not a surprise that you really needed experts who knew something about logic and linguistics to provide this form of supervision. So we thought, what if we could actually get away with much lighter weight supervision? What happens if we just have question-answer pairs? So this would be great from a point of view of collecting data because you can just ask anyone on the internet to give you examples. They don't have to understand programs. But there's one computational challenge here and statistical challenge, which is that now the learning algorithm has to do a lot more work. Given a question and an answer and a context, it needs to search implicitly over lots and lots of programs to finally maybe get the right one that executes to the right answer. And sometimes it can be like finding a needle in a haystack. So nonetheless, we were actually able to get fairly good and robust results on a lot of wide number of benchmarks, despite not having the full program supervision. But I must admit, it was pretty painful work. So in 2015, we decided, can we do something a little bit differently? This is really kind of painful. So the traditional approach to building a data set for semantic parsing is that you go and you collect, maybe from crowdsourcing, a set of questions that you would like your system to be able to answer. And then you go and annotate them with what you want the system to do, with either programs or answers directly, if you want to be a bit fancier. But the main problem is that these data sets are often small and incomplete. So for example, we had this web questions data set, which we forgot to include numerical relations, which was a pretty big oversight. So why don't we start with, instead of what the users want, we start with what we have. So we have APIs or we have databases. And each of these APIs and databases provides for us a set of primitives. And these primitives we can attach to a synchronous grammar. And the synchronous grammar can generate for us a set of program and canonical utterance pairs. So this is nice because this shows us that if you see this utterance, then this is a program. So now we have training data. But there are two problems. Problem number one is that if you read the sentence article that has the largest publication date, that's very unnatural. And that's because it's hard to generate a compact grammar that generates fluent English. And second of all, it only generates one canonical utterance and doesn't realize the full complex space of lexical variation that's present in language. To address both of these concerns, in step 2, we paraphrase using crowdsourcing. So we go to Mechanical Turk and ask crowd workers to please write these in a more natural way. And they will provide a number of paraphrases. And the nice thing about this at this point is that these crowd workers don't have to look at the program at all. They just have to read these canonical utterances. So before we had to have people annotate programs, or we had to get answers and then pass the buck down to the learning algorithm. Now we can get these paraphrases which are paired with programs, and now we have a fully supervised training data set. So we ran experiments in 8 different domains. We collected brand new data for these domains, and the crowdsourcing only took 5 hours for each domain. The results were kind of mediocre though. They were far below the state of the art. But I want to say that since then, there's been a lot of follow-up work that leverages some of this core idea, improves the representation, the modeling, and the data cleaning process, and it essentially gets much better results. So there are two data collection strategies that we talked about. One is learning from behavior. You get questions that users want to ask, you get answers which are the answers to those questions, and then you have to solve the technically challenging problem of searching over programs. Or you can start with a synthetic data set and expand out to the set of more realistic utterances via paraphrasing. But this has limits. It produces biased data and often results in mediocre accuracy, although you can imagine improving this. But it is cheap, fast, and easy. So my recommendation in practice is let's start with pre-training with these paraphrasing models and get to the point where we have a good enough model. Now we can get realistic data and fine-tune from this data and not be subject to such a hard search problem because we have a decent model already. Okay, so that's data. Let's turn to representation now. So how do we go from natural language sentences into programs? So if you take Semantics 101, you'll find that the answer is compositional semantics. You map each word into some predicate, and then you combine these predicates compositionally to produce the full program. This is kind of beautiful, except that in practice, language is much more complicated. There's many ways of saying the same thing, and in general, the mismatch between the structure of natural language and the structure of programs can be divergent. And this leads to complex grammars that are needed to bridge this divide, which is not so much fun. So in 2016 with Robin, this was 2 years after seek-to-seek for machine translation. We've already seen some successes in machine translation being carried forward by these neural models. Let's try to apply these ideas to semantic parsing. So the basic idea is rather than having a grammar, we'll just use sentences and map them into end-to-end into a sequence of tokens that is the program. And instead of having a grammar, we're going to use soft attention that allows us to form some sort of alignment between the words in the language and the predicates in the program. So there's one problem here, which is that remember that the machine translation datasets were orders of magnitude larger than the semantic parsing datasets. And so these seek-to-seek models just didn't work out of the box. So we had to do two things to make this work. First is that we introduced a copy mechanism that allowed you to look at tokens in the natural language, like Europe, and just copy them directly into the program. And this improved the data efficiency. Another thing we did was use data recombination, which allowed us is an extension of data augmentation for structure prediction, where we were able to generate new data by combining and splicing different existing data points. So with these two innovations for improving data efficiency, we were able to achieve state-of-the-art on semantic parsing data sets while using a much simpler system without the complexity of having all the grammars. Another type of representation I want to briefly discuss was work that comes out of what I did at Microsoft Semantic Machines in the context of dialogue. This is a tackle paper from this year. The idea in dialogue is that we're going to represent the dialogue state as a data flow graph, which captures all the computations that are done over the entire course of the history of that dialogue. And so now utterances are going to not just map to isolated programs, but they're going to be mapping to programs that perform additions or transformations of the data flow graph. So for example, if the user says, what's the weather going to be like during my coffee with Megan, then this is going to map to a data flow graph that takes Megan, finds a person, and finds an event with that person, and the subject gets its time and location and gets the weather. So that data flow graph represents a program that's executed for the first utterance. And now, what happens if the user asks, what about during the company retreat? So for this utterance, what we do is we map to a special revision operator that is a meta operation that transforms the dialogue data flow graph. It looks back and says, wait a minute, we basically have the same computation up here, except for instead of coffee, we have company retreat. And now what this neural model needs to predict is revise with company retreat. And what gets executed is this entire new data flow fragment. And this is a particular type of structure that you see common in dialogue. And modeling this structure explicitly makes learning much more data efficient, as we show in the paper. So in summary, representation, I think, is a really fascinating but understudied problem for semantic parsing. The general rule of thumb is that we want the representation to encode the coarse structure, like this trellis, but let the learning fill in all the details, like all the vine growth on top of that trellis, so that it can capture all the long-tail lexical variation. So now let's move to capacity. So what's wrong with existing virtual assistants? Well, they actually work quite well on a constrained set of utterances, like what's the high tomorrow in Seattle. But they basically don't work at all on many of the long tail, like how much hotter is it tomorrow in Seattle than the yearly average. And this is because they don't even try. And the main problem with these virtual assistants, in my opinion, is it's what I call capacity. So, and by that, I mean both the breadth. And by breadth, I mean here you need to access not just the weather API, but also an almanac that gives you historical averages. And even having that knowledge source available is a notion of breadth that's missing. And also you need depth, because you need to take those two numbers and be able to compare them and take the difference and do reasoning in general over that. And so if you look at the classic semantic parsing domains like US geography, they're very limited. And I remember back then when I built a semantic parser and was really excited about showing it off to people, it got 91% accuracy, so this is great. But most of the things that my friends asked of this system, it just wouldn't be able to answer, not because it was the language understanding was failing, but just because the knowledge base was too small, or it was falling out of capacity. So in 2013, we decided to try to push this as far as we could. So we built semantic parsers on large knowledge graphs such as Freebase, which had many, many orders of magnitude more facts in them. And this was great. We could handle much more of questions that people might ask. But even Freebase was not enough. There's just a lot of facts in the world which are not captured in knowledge graphs, even if they're very big. So then we looked at web tables. So these are tables on the web, and a lot of these tables have rich information in them that are not present in Freebase. And we built compositional semantic parsers on top of these because the structure in these tables gives you enough to work with to answer questions like, who was the person, how many people came in third from, a European country. But we could go even further. We also explored directly answering queries on web pages, which are still semi-structured. Maybe you have lists, or you have other sort of structured elements which are not tables. And finally, aspirationally, I think the thing that would really unlock a lot, which we only lightly dabbled in back in 2017, is this idea of building an agent that could take actions on the web on your behalf. It could click on buttons, it could type into forms, and perform actions much like a human would be able to. And that, I think, is the ultimate way to unlock an unbounded amount of capacity, although it obviously raises a huge number of challenging questions, both logistically, how do you deal with real websites, but also kind of from a modeling perspective, because the space is just so vast. So I want to emphasize that capacity is, I think, the real main bottleneck, preventing these virtual assistants from being much more kind of pervasive and dominant than they are today. But it's hard. It's a trade-off. We see cases where we can take databases and perform deep question answering on them and compute all sorts of answers, but only for a restricted set of predicates. We can also look at the whole web, and we can build question answering systems that retrieve answers, but we can't really compute much with them because there's not enough structure, and models currently don't have enough understanding of what's going on in them. So the grand challenge is, how do you have both depth and breadth? So the final topic I want to address is the question of adaptivity. So what else is wrong with existing virtual assistants? Well, it's not that they make mistakes. Humans make mistakes too. The problem is that when they make a mistake, there's no recourse on failures. So as a result, users trying Siri will discover something that doesn't work, and then they'll be disincentivized to try it again or work around it. So from a data collection perspective, what you see is a set of utterances which are near what the system can do rather than what the user actually would want the system to do. So in 2016 with Sida and Chris, we wanted to develop a paradigm that could get us out of this rut. And this is what we came up with. We were inspired by Wittgenstein, a famous philosopher of language, who famously said that language derives its meaning from use. Language is not a piece of text that sits or has just something that you look at with structure. It is something that people develop and use in a particular activity. So the meaning of language is how people use it. So let's try to take this idea and operationalize it. So we develop an environment called SharedLearn, in which we have a user and we have a system. And the user has some goal in mind. For example, to turn these blocks into these blocks. But the user can't actually move blocks around. The user has to, but the system can. The system can perform user actions on the user's behalf. So only thing that user can do is talk to the system. But unfortunately, the system doesn't understand language yet. So this user is going to start by saying something like remove red. And the system is going to say, I don't know, but here's some possibilities. And the user can select from those set of possibilities. And at this point, something incredible happens. The user makes progress towards this goal because the system has actually taken an action that the user wants. But furthermore, the system gets a wonderful piece of training example that's used to update the model that makes it more capable of understanding the user's requests in the future. So next time the user says remove red, the system will hopefully know what the right answer is. And if you iterate this process, then the user can increasingly accomplish their goals in a much faster way, while the language learning happens on the system side to help the user accomplish their goals. So we ran some experiments on Amazon Mechanical Turk, and the results were really interesting. So we had a number of players who were able to really successfully teach the system a language that allowed it to allow the users to accomplish their goals. But interestingly, the types of language that each user taught was different. Some people taught something that was more English-like. Some people used shorthand. Some people use Polish. Some people use Polish notation. Because there was no preconception of languages having to be English or German or Chinese. What we had was a language that evolved from this interaction between a user and a system where the user was trying to accomplish some activity. So then we wanted to really scale this up. So imagine you wanted to take this utterance and map it to this beautiful structure here. Now, if you apply the same techniques as before, you would have to generate this extremely complicated program which would not be guessable by the system. But what would you do to a human in this case? Well, you would probably try to explain or define what the sentence means. You would say, well, to do this, you would add a chair, move 5 left, and add another chair. And maybe the system doesn't know what add chair means, so you would say, okay, well, to add a chair, you add 4 legs, add a chair base, add a chair back. And maybe the system doesn't know what 4 legs means. And you can kind of drill down until you reach a point where the system really understands what brown block means. So here's the interface that we built. This user types in add yellow palm tree. If the system already knows what yellow palm tree is, then great. The user gets their yellow palm tree and moves on. If the system doesn't know what yellow palm tree is, then the user will get an opportunity to define what yellow palm tree is and explain it and break it down into utterances that the system can actually understand. And at that point, again, the user gets their yellow palm tree, just takes a little bit longer, and the system gets a nice training example from which it can learn not only what yellow palm tree means, but generalizations of that by some sort of grammar induction. So we ran this on a Mechanical Turk, and this time we let users just build whatever they want using the system in a much more open-ended way. And we also had every user simultaneously teach one system at the same time, so there was sharing between the users. So what we got was really kind of mind-blowing. We got all these different sculptures that people were able to build using our system. And in the process, the users taught the system lots of different things like high-level concepts like cube, paraphrases, shorthands, and in the process, this language enabled the users to accomplish their goals much more effectively. So more recently, we've been trying to take these ideas and apply them to robotics. So this is ongoing work, but we have some preliminary results in simulated robotics settings. So here a user wants to talk to a robot, wash the coffee mug. The robot says, I'm sorry, I don't understand. And the user can proceed to break this down into sentences that the robot might be able to understand. And after this interaction step, the user can perform teaching explicitly where you revisit the sentences that the system didn't understand and the user can identify the subsequent sequence of actions that maps to this initial utterance. And in the process, again, the user makes progress towards their goal and the system gets a nice piece of training data that can update the model so that the user can be more efficient in the future. One thing we're doing right now is trying to leverage much of the existing work in deep learning to make these models much more expressive. But one challenge behind using these methods as opposed to grammar-based methods is that getting the systems to know what they don't know is really hard. Because in the interactive setting, you're getting 1, maybe 2 examples at a time, and current methods are just not equipped to deal with this low data regime. Furthermore, we want to do one-shot generalization. After the user teaches wash their coffee mug, they might expect the system to know how to wash a plate, how to wash a fork, how to pick up a coffee mug. And this also doesn't fall out from kind of standard seek-to-seek models. So what we did was to develop an exemplar-based neural network which lifts the utterances into these templates and then embeds these templates and then does some kind of a nearest neighbors method to allow you to get both confidence estimation and one-shot generalization. So adaptivity, I think, is really important because it allows us to make some progress on some of these previous headaches. First of all, data was really hard in semantic parsing because in order to get a large amount of data that's realistic, we need users. And the nice thing about the interactive setting is that we situate real users in the system so that the utterances that we get are actually from users trying to accomplish goals, which is the whole point of semantic parsing. And second of all, the issue of capacity. Rather than building a system that has some limited capacity and the users kind of keep on falling off the edge and getting frustrated, we equip the user's ability to teach the system via definitions, which allow the user to expand the set of capabilities from the primitives into richer and richer domain capabilities. But I will say that learning in the interactive setting is extremely challenging. If we are not careful, we actually get systems which frustrate the user, and the user will immediately adapt and back off to using very simple language and not teach the system at all. And this happens when you have a system that's not very data efficient. There's no trust in this case. The user will not spend the time teaching the system because the system won't learn. So I think this is a really big technical challenge. How can we develop methods which are robust and can do few-shot learning? And I think those are necessary to unlock the full potential of adaptive natural language interfaces. So now let me just summarize the talk. So we talked about 4 aspects of building semantic parsers for natural language interfaces. The first is data. So data has been a long-standing bottleneck. If you look at machine translation, there's just a wealth of data sitting there and it's realistic, and that you can focus on kind of the modeling of that data. But there's no equivalent of a parallel corpus for semantic parsing because the type of data you want are real users interacting with a real system, but you don't have a real system. So it's a chicken and egg problem. So we discussed a few ideas on how to circumvent that. You can bootstrap using a grammar that generates some synthetic data set, expand it using paraphrase, or these days using large pre-trained models. And then finally, you can use adaptivity as a way to allow users to provide and teach the system more deliberately. Secondly, representation, I think, is also a very, very interesting topic. I think, especially since data is scarce in the interactive setting, we need methods which are much more data efficient than the models that we have now. And also, I think representation there's another sense in which representation I think is understudied, which is that a lot of executable semantic parsing tends to focus on this end-to-end setting where you can actually think about representation as maybe a means to an end. You can just train some sort of end-to-end model where you use whatever language or representation you want as long as you get the end goal, which might be fine for building one limited domain. But if you think about representation of language and language understanding more broadly, maybe we need kind of representations which aren't just geared towards the end-to-end setting, but are more general purpose. I think pre-training, large pre-trained models have an important role in this, but connecting that with the kind of some of the more structural elements necessary for executable semantic parsing is still, I think, a challenge. Third, capacity is, I think, the single most important bottleneck if we want these virtual assistants to be much more pervasive than they are. And this is challenging because you can have depth where you have a limited database and you answer deep questions about it, or you can have breadth which you can do question answering on basically unstructured text. But how to have both, how to get enough understanding of a wide, diverse data source and that you can do composition is a grand challenge. And finally, adaptivity, I think, offers a really interesting and exciting avenue to pursue because I think it changes the game a little bit. Instead of users being just users, they also become teachers because in establishing this adaptive interface, they can be incentivized to teach the system new tricks. And as a result, the system can learn more reliably and faster, and you can hope to get to a more personalized and effective natural language interface as long as you can do data efficient learning. So these were some open questions. I think there's a lot of work to be done. We made some progress, but I invite everyone to kind of come and think more about these issues. And I just want to end with this picture, which is that semantic parsing for natural language interfaces, I think, has enormous potential. We have this jungle of APIs and data out there, and we have all these users. And if we can only equip them with an interface like natural language, then we just lower the accessibility barrier and allow many, many more people to enjoy and harness the full power of computing. So that's all, and thanks for all your attention.